Hello everyone, I'm Lipeng. It's my pleasure to attend this conference. Today, I will present our work about how to accelerate Lattice-based cryptography with AI Accelerator. And this presentation consists of the following parts. At first, I will introduce the background about Lattice-based cryptography and Tensor Core. And then I will demonstrate some details of our design and implementation. After that, I will show the evaluation results of our prototype system. Finally, I will talk about the scalability of our solution and make a brief summary. There are many challenges in current cryptography. The quantum computer has been studied for many years. If larger-scale quantum computers are ever built, they will be able to break many of the crypto systems currently in use with short algorithms. On the other hand, conventional public key crypto systems such as RSA have been serving for many years. Therefore, new crypto systems that are secure against both quantum and classical computers are in urgent need. In 2016, NIST launched a process to pick one or more quantum-safe algorithms. Among these candidates, Lattice-based is a promising family. Formally, a lattice is a linear compilation of integers and vectors. Compared with conventional public key cryptography, they usually have a larger key size and lower performance. Generally speaking, polynomial multiplication over a ring is usually the most time-consuming part. Many measures have been done to improve the performance. Some researchers try to use a smaller modulus from the view of design and adopt fast number theoretical transform, Turing-Cook algorithm, and faster modular reduction. From the perspective of hardware, a processor with strong computing power is always a good choice, such as a CPU with AVX, Neon, or others technology. Then, the common method is taking measures according to the features and supported technologies of the platform. Thanks to the development of artificial intelligence, many vendors have designed their own dedicated processors, such as Google TPU, Apple M1, and ARM NPU. AI accelerators usually focus on low precision, low data flow, or operation mode, so they can achieve higher performance than the general-purpose processors. NVIDIA has claimed that the Tensor Core on Tesla V100 can reach 125 tensor T-flops. The tensor cores are programmable matrix multiply and accumulate units, which perform fused multiply at mixed precision. The matrix size is usually 16 multiply 16, and the input is float point 16, while the product and accumulate and the result are float point 32. CUDA provides several access methods. Developers can program them directly through warp-level matrix multiply and accumulate API. And then we intended to apply Tensor Core for lattice-based cryptography. There are two main challenges. Firstly, the float point 16, also known as half precision, is limited. Only integers between 0 and 2048 can be exactly represented by half precision, while most modulus is larger than 2048. Secondly, the operation mode is fixed and no more fine-grained control is provided. Hence, we select LAC as our target. LAC is a candidate of next PQC round 2, and the security is based on polylinear with errors. Its structure is more compact, and the key size is smaller. LAC uses a byte-wide modulus. The author claims that this can avoid the correction of NTT and get a bigger performance improvement. Meanwhile, the coefficient is suitable for the precision of the tensor core. Over the VRQ, the x to the power of n is equal to -1. For two polynomials, a and b, on the ring, the product can be written as follows. So we fix vector A, and we can say that only the sign and the sequence of vector B change. Therefore, we can expand vector B to a matrix. In this way, it will fit the matrix operation of tensor core. Moreover, matrix B can be compressed to reduce memory access. The size of matrix is n multiplied n. Then we compress it to 2n. After that, considering the requirement of memory alignment, we pad each row with 0. The alignment is 256 bits, which means 16 half precisions are required. So the matrix size becomes 2n multiply 16. During the implementation, we have utilized the shared memory. Compared with the global memory space, shared memory is on chip and has lower latency, but the capacity is limited. So we use it to cache the matrix or part of the matrix. At the same time, our prototype executes in single instruction multiple date mode, which means multiple polynomials can be computed in a round of operation. Besides, we have divided the task into several iterations. According to the CUDA block, in the iteration, we reuse the tails to reduce load operations from global memory or shared memory. We name our prototype TESLAC. Here comes our evaluation results. The performance of polynomial multiplication over the ring can reach more than 4 million operations per second. When compared with the submission work, TESLAC can obtain a speed up of about 200 times. The performance gain mainly comes from the hardware advantage. While we wanted to stress that the customer solution is the key point. Perhaps there is also a concern about its scalability, especially the limited represented range of high precision. We think that multiple precision representation can overcome the obstacle. Other techniques, such as Cryptography, can also be used. The potential real-world applications will be extensive. For instance, data center and CA organization, which have the need of high throughput due to the better performance per watt, is also a good choice for smart devices equipped with the similar accelerator. So let's make a summary here. Lattice-based cryptography needs a high-performance implementation. Meanwhile, AI Accelerator contains extraordinary computing power, but it can hardly be applied for cryptography due to the dedicated design. In this paper, based on NVIDIA's AI Accelerator Tensor Core, we have taken many adaptations and optimizations to implement LAC and get impressive acceleration. Moreover, with more techniques such as multiple precision representation, Cryptography algorithm, our solution can also be extended to other lattice-based cryptography, of which the modulus could be larger. With the procedure of replacing traditional crypto systems with new generation quantum-safe algorithms, we believe that AI accelerators can become a widely used, high-performance cryptographic computing platform. And there is more work needed to be done. So that's all. Thank you.